on the board. I know exactly where you got those from.
All right, if you have not already turned in your exam wrapper, please do so. Those are due now, not at the end of class. If you decided not to do the exam wrapper for exam 3, that is fine. I still highly encourage you to go through the process of doing the exam wrapper, even if don't have it up to the place where you think you want to turn it in for credit. Going through that process will really help you master the topics that you need to do so well on, or maybe you didn't have enough time for exam 3. All right, go ahead and figure out how to answer this question. It relates to your lab. I'm trying to prep you for lab a little bit. Some of you have already started working on it. So go ahead and take a minute, work with your neighbor, try to figure out how to determine what the pressure will be when we combine these two containers. All right, we have 19 clicks, 19 responses. We have more than 19 people. We probably have, 35, 40? It's a Wednesday. Not raining.
Yeah. Don't
You guys should grow up in Seattle or somewhere that has a bit more rain.
Been there for 4 years.
Yeah, so this is
Sunny and rainy every day.
Yep, great. I guess I shouldn't say it, you guys should, because you're the ones who are here. You guys are off. What?
We don't want to miss a class, otherwise we'll fall behind.
You're paying for it. Why not come to class? All right. Mondo, that looks very thin. Does that have your exam with it? I need to see what you got wrong in order to understand how you corrected it. Yeah, so think about it from my side a little bit, on that side. All right. Let us see what you guys answered. Closing out. 36 people. All right, we have a few responses. Thanks. We have a large majority of the class saying 752. I should have done alphanumeric. Why? Okay, so the unit is really important. We could say one atmosphere. Well, that'd be close. So I want us thinking about units as well as the numerical value. So can I have someone talk through how they concluded their answer? And I want it from a molecular perspective. Josh.
Oxygen and nitrogen are non-reactive gases to each other. So if you combine them in another container, there's going to still be individual gases of oxygen and nitrogen in the same container.
Okay, great. And then how does that relate to pressure from the molecular description of pressure we've been using? Joey, I like your physical drawing there. Do you want to describe what you're showing?
You're still going to have the same amount of oxygen hitting the walls, creating the pressure from the beginning to the end at the same amount of nitrogen.
Great. So what does that mean about...
They put that together to be better. You're still going to have the 159 millimeters of mercury. Yeah.
Okay, so I think what you're getting at is that if we look at any side, any part of the container, any side of it, that we're going to have collisions at a certain frequency of oxygen molecules with the same mass, right? There's an average speed of those collisions of oxygen molecules. That's still going to be happening over here when we combine the two. We have a certain frequency and speed of these collisions with nitrogen molecules at a certain average speed. Which one is going to have a higher overall speed? Do you think? The nitrogen or the oxygen molecule?
Temperature.
They're at the same temperature? So which one's going to be moving faster on average? Nitrogen or oxygen molecule? Nitrogen N2 weighs 28 grams per mole. Oxygen weighs 32 grams per mole. So they all have the same energy. That means on average, nitrogen is going to be moving faster. But their collision force is going to be the same because that's the kinetic energy. So if we have all of those happening in the same space, then the pressure is going to be the sum of those two pressures. Have you guys, do you know the term that describes this? Someone's theory?
Dalton's law.
Dalton's law of partial pressures. Okay, it's really simple if you think about the molecular side of things. You think about the molecules colliding inside, and that's where pressure comes from. All Dalton says is that if you have multiple gases, and you know the proportion of each one, you can figure out the partial pressure because it's that fraction of the total pressure. So it's this idea that if you have a constant volume and temperature, the collision frequency and force and all that stuff, the pressure in each one of these is summative. You can add up the pressure of one container and the other. If you combine them into the same, you're going to have the sum of the two pressures as your total pressure. So I think this, if we show this first, then you're like, wait, what are you talking about? What pressures? We're just having an equation, right? But almost all the class answer the first question, right? So just use logic to answer questions related to gases, if they're ideal gases. So what I want you guys to be able to do today, by the end of the day, is explain how water vapor influences your gas collection in lab, using the idea of Dalton's law of partial pressures. And then we're going to spend some time doing thermochemistry. So that means talking about endothermic and exothermic reactions, heat of a reaction, energetics of a reaction. Please tell me that you all brought your activity 34 and 35 from class last time. We'll get into that in a minute. We're not starting it yet. If you forgot, I have a couple extras, but I don't have enough for everyone to have one. All right, and then we're going to be talking about, we're going to start going to calculations. Your guys' pre-class work, which is chapter 5.5, gets into finding the change of enthalpy of a reaction. And we're talking about atomic combination and breaking of bonds in order to figure out what the reaction is. And every time we talk about these two things, did you guys notice the units are per mole? So the change in enthalpy is 36 kilojoules per mole. So if we do it for 2 moles, it's going to be twice as much energy. 3 moles, 3 times as much energy. So we're going to use that, talking about per mole, using that to look back at if we have a specific mass of a substance that reacts, how much energy is going to be released. We have to figure out how many moles there are, and then we can go ahead and do that calculation. All right, so let's go and think about your lab for a minute. I want us thinking we're going to be collecting a gas over water. So I want you thinking about, we're at room temperature. Do we have any water molecules in the gas phase? Go ahead and click in your response. All right, we have 2-to-1 response. Find someone who has a different answer, see why, and see if you still agree with your first decision. Eric, you want to grab, there's a sheet on the way in. And I need your exam wrapper if you're returning that in. All right. By the way, something I should mention, because I think this is about right, but if you are able to log into Clickers from home, don't. The point of Clickers is for me to see who's here. It's in-class participation, it's not participation in general. So that is not something that I accept. So if you have in the past responded from home when you're not here, then please email me, let me know what days so I can remove that so it's not a concern of academic misconduct. And for the people listening to the recording, that applies to you guys as well. So when you miss class, you need to watch the YouTube video. You need to complete, to watch the YouTube video with the worksheet that I upload onto Blackboard to make sure you're caught up with class. And then if you have any questions, you can ask me.
Also, there's a way you can set it to where you can only join if you're within the vicinity of the class. Mr. Two knows how to do it.
Yeah, I thought I had that turned on. I don't. I found out today. So I will make sure to try to change that. But then I've also heard that if you do that, it can block people from joining sometimes if they're on their cellular network or something else, if they're not on Wi-Fi. So I don't know that I want to go that route, but I can if I need to. All right. So we're thinking about this. We had a significant shift in answers from 2 to 1 to almost all one answer. Can I get a new voice? Someone that hasn't talked too much? Describing why you would say yes or no for this question. Maybe give an example of something that you see every day or another way of thinking about it. Angel?
I said yes because if you were to leave the water there for an extended period of time, it would start to evaporate.
Fantastic. Everyday logic, right? We know that it rained outside. Is it still wet everywhere? So on concrete, water evaporates, doesn't get soaked in. Maybe in dirt, you can think maybe the water soaks in, but water dissipates over time. If you have a cup, you leave it out, it might be gone in the morning, or a couple days later, it'll be gone. Why? Why is that happening? What's going on? We're not boiling the water, right? We're not giving it enough energy for that water to boil. So why is water becoming vapor at room temperature? Talk to your neighbor for a second. Try to answer that question. I'm going to cold call this one. I'm going to call in a random person, so make sure you have a answer for why it is that at room temperature we can have water molecules in the gas phase. All right. I heard this group having an interesting conversation. Can I have one of the three of you describe? Dawson, Kyle, Savannah.
Okay, so you explained to me sometime last week that not all molecules are going at the same speed, and but it goes out to an average speed, but some of those molecules are above average, and with enough energy, they can shoot out from being in a water state, being a water vapor state. Great.
So let's zoom back into part of your statement, and we'll kind of break it down piece by piece. So the first part is, why is water liquid? Why do things stay so closely packed together? What's happening with them there?
The intermolecular forces that are basically attracting the hydrogens to the oxygens in between molecules.
Okay, so we have one water molecule, another water molecule. The hydrogens and oxygens have partial positives and partial negatives on one that are attracted to a partial positive and partial negative on the other molecule. And so those interactions kind of hold them somewhat together. They keep it as a liquid. And those molecules that are liquid are moving around. They're constantly moving. And their speed is related to the energy. And as Dawson said, the average energy changes when we warm up or cool down a sample. But that doesn't mean that all the particles, all the molecules have the same speed. So maybe I'll do it up here on this guy if I can find my pencil. So if we're thinking about water molecules that have a very different amount of speed, if we look at one sample of gas, we can look at the number of them at each speed. And we can say at a particular temperature, we have a distribution of molecules at all different speeds. If we warm it up, what's going to happen to this graph? So it's going to go faster speed. Speed is to the right, so that means this graph is going to flatten out and shift to the right a little bit. We're going to have more molecules moving at a faster speed. The average is going to get a little bit to the right. And so one of the things we talked about in office hours when Dawson and Matt were there was, one way I think about this is that with all of these attractions between the water molecules, there's a certain speed that they need when they reach the surface. If they're going faster than that, then they're going to overcome that partial positive, partial negative interaction between the two. And if they have more than enough speed, then they can fly out of the liquid and go into the gas phase. If they don't have enough, then they'll get pulled back into the water and they'll keep moving around within the water. And so that speed required when you get to the surface to have enough momentum to carry you beyond the interactions of the other molecules is, we can refer to as vapor pressure. Or it is related to vapor pressure. So in order, if we have, in this case, we have, 5% of the molecules that have enough speed to overcome the intermolecular forces when they get to the surface to become a gas. What happens to that fraction of molecules that can overcome the intermolecular forces and become a gas when we warm it up? Talk to your neighbor for a second. What happens to the amount of molecules that can go into the gas phase when we warm up the sample?
What was the term you used for when they overcome molecular something pressure?
Vaporization. And so vapor pressure is how much of that pressure comes from the liquid. I'll get back to that in a second. All right, can I hear from a new pair or a group? What do you expect to happen to the number of molecules that can go in the gas phase when you warm it up, and how can we justify it with this graphical representation of the speed of molecules in that sample? Matt?
Okay. The area to the right of the line of vaporization underneath the curve is how many total molecules you have able to go into a vapor state from a liquid. So as the area underneath there becomes greater, as the curve pushes to the right, therefore you have more water molecules that are able to go into the vapor state.
All right, so as we have a warmer temperature, we now have a larger percentage that have enough speed when they get to the surface to overcome the intermolecular forces, to become gaseous, to become a vapor. Does that mean we break apart hydrogen and oxygen inside of a water molecule? What kind of a change would that be? Okay, we're not talking about a chemical change. We're talking about the physical interaction between two water molecules, that once one water molecule passes by the other, if it's going fast enough, it can then be a water molecule still in the air. So we talk about humidity. We talk about steam. These are all different ways we can look at water vapor with a water molecule still floating around the air. So if we have a water molecule in the air, if it's warmer, we're going to have more of them in the air. If it's colder, we're going to have less. Do you think that's a pretty standard thing we can look up? How much water vapor is in the air? Let me see what diagrams I have here. So let's go ahead and think about which of these three do you think is the best representation of the warmest sample? And then I'm going to ask one more question around this. A couple more seconds. So we're talking about the warmest sample. Check with your neighbor. We're at a 2-to-1, 3-to-1 split right now. Find someone who disagrees with you. 1 in every 4 people disagree. 1 in every 3 people disagrees with you. Couple more seconds. All right, can I hear from a new voice? Which one of these do you think and why? Aaron?
I think we agree, because it's important that the jar is capped, because that means that it can't, like, once it hits a certain amount of vapor within the top of the jar, it seeps back down to the bottom. So figure 3 shows a good amount of vapor both in the air but also moving back into the water of the jar.
Great. And so because it's at a warmer temperature, it means we're going to have more water molecules that are capable of going up into the gaseous phase, and so you can see a lot more particles up there. But then it also, because it's capped, it shows a lot of them. Once those gas molecules bounce around, if they hit the water, then they're going to go back into being in the liquid phase. Which one of these do you think is going to have a higher vapor pressure? Vapor pressure is the pressure over a liquid of that liquid itself. Which has a higher vapor pressure? Think about our molecular definition of pressure. Go ahead and talk to your neighbor for a second.
So is figure 3 the one with the warmest solution?
Correct. So then the second question is, which one has the highest vapor pressure?
Second one's lower.
On the sheet.
Say again?
On the sheet, second.
Oh, do I actually have this as a clicker question?
Yeah.
Let's change that then. Let's do... Okay, let's answer the question on your sheet. Which number is this? Question 5. Go ahead and answer question 5. Which one has the lowest vapor pressure? Please check with your neighbor. Five or 10 more seconds.
So then what do you do?
All right. Justification. Which one has the lowest pressure and why? Can I hear from Taylor or Maggie? You guys have any thoughts on this? You want to share? Okay. Can I hear from another voice, John?
I would put A, number one, because it's the coldest. So it's going to have the fewest water molecules in the air.
True. But then how does that relate to the pressure of that vapor? Let's take it one step further. So it has the fewest molecules in the gas phase because it's colder. So then what does that mean about the pressure? Do you want to keep going?
I'll pass.
Angel?
I was thinking there would be less collisions.
Okay, if there's fewer molecules, there's going to be less collisions. Great. And there's one other thing to add to that, Eric?
The collisions will be slower.
Slightly slower because that gas is at a lower temperature as well. All right. So then the big question, the big take-home question for this here, how is this relevant to your lab? Raise your hand if you have not even looked at the lab for the upcoming week. Okay. Someone who has been in the lab, can you do a really quick 20-second description of what's happening and how this is, we'll talk about how it's relevant in a second. Can you just describe the lab? I know a number of you were in lab yesterday. Aaron?
Well, you have to be able to figure out what the vapor pressure of the water is within the tube before you can figure out how much hydrogen gases will be put in the reaction.
Okay, and can you take one step further back? So what is the lab? What are we doing and collecting? And
So the lab is about reacting a strip of magnesium solid with hydrochloric acid to produce hydrogen gas and magnesium chloride salt.
great. And you do it underwater? And so then how do you collect the hydrogen gas?
The hydrogen gas is collected in an enclosed tube. I can't remember the name of the system that we set up, but you put the hydrochloric acid inside of this tube, and then you fill it up with water, and it kind of creates the separation layers. And then you add your strip of magnesium metal, put a stopper on it, and turn it upside down, and put it inside a larger kind of beaker of water, so that it equalizes the pressure of the water in the tube, as well as the pressure of the water within the larger beaker. And then as the hydrochloric acid sinks towards the bottom, towards the magnesium metal, it begins to react and produce hydrogen gas.
Thank you, Aaron. All right, so in your lab you have a very fancy apparatus like this. This is regular water. You put hydrochloric acid inside of this tube, right? And then you have a little strip of metal zinc in here. There's a hole in the bottom here so that you can have pressure equilibrate so that this fluid can go in and out. But as your chemical reaction occurs in here, the magnesium reacts with hydrochloric acid, releases hydrogen gas, which bubbles up to the top. And then this started completely full, and the liquid moves down and down and down as you form more hydrogen gas. So why is it important to think about vapor pressure of your water in this case? Dr. Neighbor, why would vapor pressure be an important part of understanding what's going on here? I want you to think about what the gas is in that top of the tube, and then how that's going to influence our calculation.
How it adds up. And so we different gas.
So question number one, what's in the top of the tube? So there's no air because we emptied it first. It was completely full of water, HCl. So what is specifically in there? Hydrogen gas, is that it? Are there any other gases in there, Caleb?
Yes.
What gas?
The gas we started off with.
What gas did we start off with?
Water vapor.
Okay, so we didn't start with any gas in there. It was completely filled to the top with HCl solution. So I'm going to disagree with that part of the statement. But then as that starts to fill with hydrogen gas, What's the second gas that fills it and why?
Water
Oxygen.
Is that Josh?
It will be water vapor once, is that it's free flowing at the bottom, right, so it can gravity and go up?
Yeah, and all this is hydrochloric acid dissolved in water. So, going back to what we were thinking about earlier, how many particles are in the gas phase? When there's no gas interface here, where it's just liquid the whole way, there's no real reason why we're going to have water overcome the intermolecular forces. It can't go beyond that and become a gas. But as soon as there's hydrogen gas here, now the water molecules, as they move around in the solution, some fraction of them will have enough speed to overcome the intermolecular forces and become a gas up here. So that top part is a mixture of hydrogen gas and water vapor, or water molecules in the gas phase. So in order to do our calculations to figure out how much hydrogen is produced, we then have to go back and think, well, how much of that's water vapor? And that's called the vapor pressure that we were talking about earlier. So if you can figure out the vapor pressure, you can look it up in a table. You can figure out at this temperature, this is the partial pressure of water in the air. We can use that to figure out our calculations. So one way to kind of look at it is that this is a different setup, same type of reaction. But what I want you to focus on is that in the gas part, not only do we have hydrogen molecules that were formed, we also have water vapor that came from the interface of the gas and the liquid. All right, that's a lot more time than I expected to spend on this. So let's transition and go to our Chem Activity 34. We worked on critical thinking questions 5, 6, and 7. I want you to go ahead and start on exercise on page, 197 at the bottom of this thing? And if you don't have your packet, I have a few extras. We're going to try to go through this as quick as we possibly can. So please make sure that you are working with someone else. If you're sitting by yourself, please move. Sit with someone else. Does anyone not have a packet from class on Monday that needs one? All right, I'll give you guys about 2 or 3 minutes, and then we'll talk through exercises 1, 2, and 3. Sorry, exercises 1 and 2. So we're doing Model 2, exercises 1 and 2. So the third page.
We already did that.
We did critical thinking 5, 6, and 7. If you've completed that, then go ahead and keep moving forward. At no point in time should you be sitting and idle. If you finish the thing we're talking about, move on to the next one. almost everyone is done with exercises 1 and 2. So can I have quick shout outs for 1A, endo or exo?
Endo.
Why? That's another review? Every time we break a bond, those are together because they fill each other's octets. They're more stable, so if we break them apart, we have to put energy in. What's the sign of delta H in that case? It's a positive delta H. All right? So what about B? Endo or exo? Exo, which means delta H is? And C? That releases energy when those two come together. So that means it's going to be a negative delta H. All right? So go ahead and let's start working on the next page, Model 3. And by the way, one quick announcement that I need to make is for the spring semester, if you decided to take Gen Chem 2 with me, it's obviously a night class. At first, when you tried to register, you could only sign up for the night lab. They've fixed that, and so now you can take any lab and still be in the night class. So if you sign up for a night lab and you don't want to be in the night lab, please change because it's one, it'd be great if you take another time. And two, some people can only take night classes because they work, and hence the night lab works really well for them. So if you have it in your schedule and you can take a day lab, go ahead and look at your other options. There are 2 other lab types. So right now the night lab is filled, but I think part of the reason is because...
It wouldn't let me register for your class because...
Correct, that has been changed. So now you can register for my class in any lab, they fixed that, and the night lab is filled right now, but I suspect it's because people had to at first. And so if you can take one of the lab times, go ahead and do that so that the night lab is available for people who can only take the night lab. So check your schedule, see if any of the day labs would work with you. If you're on campus anyway, then look into that, please.
Did they do away with the Monday lab?
They did away with one lab, so now there's only 3 labs. There just aren't enough people signed up, and so, or maybe not enough graduate students. I can't remember which one of the 2. Careful, O2. So think about energy on breaking on forming or 2 oxygen atoms, the same as O2.
Yeah.
Okay, so what about energy? So you're going to want to compare O versus O2. Versus one of those. That's not. Did you have them delivered for you? Make sure you're carefully reading through all the text in Model 3, answering critical thinking questions 8 through 10.
No.
So I'd highly recommend talking through your thoughts on this.
Okay.
If Diana's available for that, you'd be great.
Okay. Read it. I haven't been able to read it on this section. Number 8. Why is changed?
Because they're unbounded.
Okay.
They're just in their own state. So there's no energy required.
Because they're not bonded. And then when they're bonded, okay, that's what they're choosing.
And then, for molecules where all the values are entities of atom combination negative, nitrogen has a triple bond, and oxygen has double bond, so bond strength is higher than nitrogen, so it requires more energy to break that bond.
Okay.
One of the elements say to do the brand new one that's being built in the next 10 years. How it works. Right? See a black hole, we all have it. One black star. The theory is
Oh, sorry, no, but it's
All right. Take about 30 more seconds. We're going to talk through questions 8 through 10. Write down any last thoughts. All right, can I hear a couple different ideas of why, if you look at that table, delta, the enthalpy of atomic combination is 0 for the elements by themselves? Caleb?
Because it's there now, the enthalpy of formation for an element N is going to say it's just 0.
So there's one thing that's really interesting about this is it totally depends on how you define it. So if you define 0 as the individual elements, you know that you're going to release energy to form any molecule, and so it's going to be a negative value. so you're talking about delta H formation. That's not what we're looking at. We're looking at delta H atomic combination, AC. So formation, it's not going to be necessarily 0. Why is it 0 for atomic combination?
Because it's not a combination. It's not one.
Great. So the definition is just, it's like saying, how high are we off the ground? Well, we're going to define that based on sea level. That's 0, and then we're either above or below that. That may or may not be relevant to what you're talking about. For this particular thing, we're saying, well, if we know that we're really interested in the change of enthalpy, right, either one way or the other, of a reaction, all we really care about is making sure that relative to each other, we know the difference between them. So we're going to call these 0. These are all the individual atoms. And so to find that, we're going to say that this is the delta H of atomic combination. They're not combined, there's no combination, so that's our 0 point. As we combine multiple atoms together, we're going to see a change in enthalpy. And that's the enthalpy of formation, going back to what Kayla was saying. So the enthalpy of the reaction, or enthalpy of formation, there's a number of different ways, or just sometimes we call it enthalpy, delta H. But the atomic combination, that says we're starting from the atoms, and when we take those atoms, what did we find for delta H of CH4? What do we have for that? Negative, what did you say? 1,662 kilojoules for every 1 mole that's formed. So in our defining this as 0, we say that when we combine 4 hydrogens with 1 carbon, we form 4 bonds. This is how much energy is released. Is the difference between delta H of the products and it's all relative. Your homework might be showing you that this delta H is not 0 for individual atoms. But then this value down here is going to be, this might be 0. If this is 0, then each one of these would be a quarter of that. And so the difference, this is still going to hold true no matter what our 0 point is. You're going to have to kind of see this as you go through. Because I get a lot of confused looks. So as you're calculating, we'll talk more about this on Friday. All right, so let's go back. Question number 9. Why are all the enthalpy values for atomic combination negative? Go ahead.
It goes back to kind of the same concept as it would be 0 there. Now that there's a combination, to make that bond, you have to, it would lose. Well, no,
It would evolve, I think is the word your homework uses. It would evolve energy. So because our definition of 0 is individual atoms, when they do combine, we know we're forming bonds, that the total change is going to be a release of energy, an evolving of energy, which is a negative delta H. All right, so if you draw the Lewis structures for N2 and O2, how are they consistent with the values in the table? I'm going to go ahead and draw those out over here real quick. Anyone figure out what they're asking here? Logan?
So it shows that it takes more energy to break the N2 bond, and that makes sense because it takes more energy to break a triple bond as opposed to a double bond.
Okay, great. You're actually thinking about it the exact opposite way of how it's described. It's really useful to think about it both ways. So delta H atomic combination here is what, negative 950 something? I don't know. And this is about negative 620 kilojoules per mole. This says if we start with an oxygen separate from an oxygen, the total change is a release of 620 kilojoules for every 1 mole of O2 we form. For N2, for every N and N separate, and we form an N2 molecule, it releases more, 950 some, whatever the number is, kilojoules per mole. And the reason it's more is because this is a stronger bond that forms. It releases more energy in the process, and conversely, what Logan said is absolutely true. To break them, we have to put in that amount of energy. It's going to be a harder bond to break because it is more stable, and it's going to require more energy to pull those atoms apart. All right, we will continue with this on Friday. I might send an announcement out that we need to do a tiny bit of it before class, because I think you guys can probably do the next couple questions, so I'll send that out, and then we'll keep working on this on Friday.